Greetings, I am Elizabeth Berg, a PhD candidate in the Department of Geology and Geophysics at the University of Utah. Welcome to my PhD defense, Seismic Tomography of Southern California and Alaska via Bayesian joint inversion. My committee consists of my advisor, Professor Fanchi Lin, and Professors Mike Thorne, Amir Alam, Pete Lippert, and Yehuda Ben Zion. Thank you all for joining me today to hear what I have been up to during my PhD. The last year has been quite chaotic, and I know many of you are coming from across the globe, and I greatly appreciate all of you. My PhD work focuses on performing seismic tomography to image the interior of the Earth using seismic waves, specifically in the near surface, crust, and upper mantle, or 100 miles or so beneath our feet. We are imaging both Alaska and Southern California, with each region outlined in white here. Why Alaska? Alaska is home to high seismic hazard and complex geology, making it tricky to characterize the subsurface and hazards. On the left, you can see the massive damage to the road during the 2018 Anchorage earthquake, but the 1964 Great Alaskan earthquake was 100 times larger. Damage is shown in pictures on the right. Southern California is also home to high seismic hazard and plenty of massive faults with potential for large earthquakes. On the left, in Los Angeles from the 1994 Northridge earthquake, we can see some major damage. On the right, we have a simulation of a possible realistic earthquake beginning on the southern end of the San Andreas Fault, shown in red. As you can see, downtown Los Angeles gets extremely shaken up because it's in a sediment basin that will reverberate and amplify seismic waves. In the case of a large event, emergency responders need to know where to direct the majority of their efforts, which will depend on knowing where shaking has occurred the most. Where did tomography models come in? Tomography models and seismic imaging tells us about the geologic past by showing us a snapshot of what is beneath our feet today. It also plays a key role in ground motion simulation, hazard analysis, and emergency response. The U.S. Geological Survey uses both fault and tomography models to determine where there is highest hazard. My motivation is to use regional scale deployments, including from the EarthScope transportable array in Alaska, and networks to create regional scale models of the subsurface with sensitivity from less than 1 kilometer depth in the shallow crust into the upper mantle in Alaska, and in the near surface and crust of Southern California. This also enables us to cross-check our shallow results with previous small-scale studies and connect the shallow to depth. We use multiple data sets obtained from teleseismic earthquakes and ambient noise cross-correlations through a Bayesian joint inversion Markov chain Monte Carlo that enables us to quantify sensitivity and uncertainty. Let's discuss the data and methods that I use to accomplish imaging the subsurface. We use Rayleigh wave phase velocities, or the speed of the Rayleigh wave propagating through a medium. A Rayleigh wave is one of the large surface waves that you really feel shake the ground in an earthquake and has a retrograde rolling motion like a backwards water wave. We break down the Rayleigh wave signal into multiple frequencies or periods where higher frequency or shorter period has shallow sensitivity. We show this in our sensitivity kernel, where we show sensitivity versus depth from the surface to 40 kilometers. We see that where the amplitude is largest is where the greatest amount of sensitivity lies. You can see that this is shallower depths for shorter periods and deeper depths for longer periods. One of our other data sets is Rayleigh wave ellipticity, or horizontal to vertical H/V ratios, which measures the shape or the horizontal motion versus the vertical motion of the Rayleigh wave at a specific station or location. As shown in the sensitivity kernel, H/V is sensitive to much shallower structure compared to the phase velocity for the same period. Again, we are showing sensitivity of the H/V ratio versus depth. As we mentioned, we use Rayleigh waves with the retrograde motion moving through the subsurface, but we don't use earthquakes for our source. Instead, we use a technique called ambient noise cross-correlation, which takes advantage of the ocean waves hitting the shoreline and other sources that put energy into the earth. If this energy arrives at one station and passes through the subsurface to another station, we can use cross-correlation to obtain the seismic wave as though one station is a virtual source and the other a receiver, and obtain the Green's function, which includes a Rayleigh wave. The signal is extremely small, so we have to stack days and days of continuous recordings in order to constructively interfere and amplify our Rayleigh surface wave to measurable levels. We also take care in processing to maintain the relative levels on the vertical and radial components so that we can correctly measure H/V ratios. That's all well and good, but what does this cross-correlation to obtain a Rayleigh wave look like in real data? Here I am showing a longer 16-second period Rayleigh wave from the source station DHY near the Denali Fault to all other stations. DHY again is acting as a source and all their stations as receivers. You will see the Rayleigh wave collapsing onto the source station and then moving out from the source station to all other stations. If you focus on a single location, you can see that retrograde elliptical backwards rolling motion. The seismic waves at the bottom here correspond to the station that's the triangle on the western side of Alaska. Once we have our measurements, next we need to use them to understand the subsurface. Here I am showing an example shear velocity model beneath a single station in the Los Angeles Basin. Shear velocity is a physical property that captures the shearing motion of a medium. Slower shear velocities are seen in basin sediments, such as the Los Angeles Basin, where the loose particles are not as easily sheared. Crystalline rock in mountains, for example, though, has higher shear velocities. Our 1D velocity model, directly beneath the station shown here, consists of shear velocity versus depth. This contains a top linear layer, a crustal layer with a curve described by crustal B-splines, and a mantle layer, also a curve consisting of B-splines. B-splines are a series of parabolas that we shift the amplitudes of and combine in order to form a curve with just a few values. So we change the heights of the different color curves and add them all up to create the bold black curve. Our starting model is the Southern California Earthquake Center model S4.26 from Lee et al. 2014, and our Markov chain Monte Carlo inversion is based off of Shen et al. 2016. So what is Markov chain Monte Carlo? We've already described our starting model M0. Bayes' theorem relates the posterior distribution to the prior via the likelihood function. We define the prior or search area for each model parameter based on a range and Gaussian width from our initial model parameters with details in the table. To visualize this, we have an example of the distribution of the sediment thickness parameter for the prior, which I've outlined in orange, and the posterior, which is outlined in blue. The posterior, it contains all models that will roughly fit our data. In order to form the likelihood function and determine those posterior models, we must forward model a given shear velocity model via Hermann's computer programs in seismology and determine the expected data values. Here we show the result of forward modeling the starting model M0 and the result for the predicted H/V, shown as period versus H/V, and phase velocity, period versus phase velocity. Note that these are all black triangles. Our actual data is shown as black circles and bars, with the bars denoting uncertainty. Next, we calculate misfit of our prediction to the data, and the combined misfit, which is a value of 15, is given as the equation S and input into that likelihood function. We walk through the model space using the metropolis law, which uses the likelihood function to determine the probability of acceptance, where we accept a newly generated model if it has higher likelihood or lower misfit. And a certain percentage of the time, we randomly decide to keep a model with higher misfit in order to avoid becoming stuck in a local minimum. That's all a bit technical, so what are we really doing? From our starting model M0 with a high misfit of 15, we create a new model M1 by slightly randomly perturbing the parameters that make up M0, as previously shown, creates our prior distribution. So this gives M1. M1 has a lower misfit, so we will again roll the dice, it is a Monte Carlo, and perturb the parameters slightly from M1. This gives a model M2. However, after we forward model and calculate misfit of M2 predicted data to observed data, we find M2 has a higher misfit than M1 and lower likelihood. We now restart from M1, not M2, and again, slightly randomly perturb M1 parameters to obtain model M3. We now use model M3 and slightly randomly perturb its parameters to get model M4. Although model M4 has a higher misfit, we may randomly decide to use this model as a starting point anyway in order to avoid local minima and not get stuck anywhere in the model space. In this case, we slightly perturb M4's parameters to obtain model M5. We repeat this process over and over, and the set of models produced forms the Markov chain. For our 1D Markov chain Monte Carlo inversion, we create 10 Markov chains, each starting from our initial model and exploring 3,000 models, walking through the model space following the Metropolis algorithm. This gives a total of 30,000 models. We determine the posterior using a minimum misfit threshold set from the model with the absolute minimum misfit. In other words, we figure out what models all roughly fit our data. So let's go back to our 1D model in Los Angeles and see what this looks like. Reminder that we have our shear velocity versus depth on the left, and our h over v as period versus h over v, and phase velocity as period versus phase velocity. So model on the left, data sets on the right. We repeatedly walk through our model space and test different models, and at the end we keep all models that roughly fit our data equally well. So here's our model search space in green, and our posterior models are shown as multicolored strands with the corresponding predicted models shown on the right. As you can see, we are fitting our data. Now that we have the fundamentals down, let's zoom into Southern California. We're focused on Southern California as it is a region with complex geology and high seismic hazard. As you can see in the simulation, seismic energy is trapped and amplified in basins, such as the Los Angeles Basin and in the southeast corner of the Salton Trough. The California velocity model is based on full waveform tomography, which is limited at shallow depths. That's where we come in. By providing shallow resolution, we can answer ongoing geological questions and help with hazard analysis. Our specific questions are, do we observe major features, including the basins, Central Valley, Los Angeles, and in the Salton Trough? Do we also observe mountains, including the Coast Ranges, the Peninsular Ranges, which are to the south, and the Sierra Nevada Ranges? How do we connect the subsurface geology to the How do we connect the surface geology to the subsurface? Can we gain regional constraint on the basins and see changes across the major faults, including the San Andreas, the San Jacinto, the Elsinore, the Garlock, and the San Andreas to the north? We use 315 stations across Southern California, maintained by the Southern California Earthquake Center, or SCEC, and various Southern California institutions. We perform 9-component ambient noise cross-correlations with care to preserve relative amplitude information in order to extract H over V data. Here we have an example of the waveforms recorded on the radial, or horizontal, component and vertical components between station FMP in the Los Angeles Basin and WBS in the Sierra Nevada mountain foothills. We can look at the expected H over V by looking at the particle motion for both the receiver station on the left in the Sierra Nevada mountains and the source station in the LA Basin on the right. As you can see, one is elongated vertically and the other horizontally. The LA Basin station FMP is elongated horizontally because of the contrast between soft sediment and bedrock, which promotes more radial motion. We measure the H over V ratios by taking the envelope of our signal at a specific frequency and then finding the maximum of that. We perform this analysis for every station pair and combine the results at each individual station to determine that station's H over V ratio and uncertainty. Again, we expect high H over V in sediment basins and low H over V in crystalline rock. Here are our results at each station for 7 seconds period, which is sensitive to around 1 kilometer depth, and 15 seconds period, which is sensitive to around 3 kilometers depth. Our observations include high H over V, which is purple in color, in the Los Angeles Basin, Salton Trough, and Central Valley. We also observe low H over V in the mountains. In general, with increasing period, we see lower H over V as we move past the sediment-bedrock interface. We interpolate the results between stations via Gaussian smoothing to have results and uncertainties spanning the entire region and not limited to each station. We also have Rayleigh wave phase velocity measurements across the region provided by Dr. Hongwei Chiu, previously a PhD student at USC and now a postdoc at Rice. Observations from this data include low phase velocities in the sediment basins and high phase velocities in the mountain ranges. Again, we use a CVMS 4.26 as our starting model and focus on perturbing the near surface and crust using our HRV and phase velocity datasets across multiple periods. Next, we will look at the inversion at the station in the Los Angeles basin we reviewed earlier and a station in the mountains. On the left, we have the Los Angeles basin station starting model, predicted HRV and predicted phase velocity, as well as our data. On the right, we have the Peninsula Ranges mountain station. If we only use the phase velocity data set, we will not have as strong of a constraint. These are the posterior and final models if we don't include HRV data. However, if we do include the HRV data, we have a much tighter distribution in our model space. Note that you can also see where we lose sensitivity at depth, as the range of models below 30 kilometers depth spans the entire search range for the Peninsula Ranges station. We apply this technique to every location in the region and obtain our final shear velocity model results across the region. Here are our results at 0.5, 2, and 9 kilometer depths. Note that the color bar changes with depth in order to capture the different regions. We accomplish our goal of observing major features, including low shear velocities in the basins and high shear velocities in the mountains. We also observe the depth of the LA Basin, and you can see clear contrast across faults, including constraining the Mojave Desert across the Garlock Fault and San Andreas faults. When comparing our result to the CVMS, where red corresponds to our result being slower and deep blue to our result being faster, we see that we have similar results in the LA Basin. This is excellent, as the LA Basin is very well constrained by the CVMS model. We do have clear, well-defined edges in the salt and trough sediments, and our results are a hair faster in the Sierra Nevada and Central Valley. We have multiple cross-sections through our model, but for the sake of time, I am going to focus on AA prime. The top shows our model in the upper 10 kilometers, and the bottom shows the difference between our result and the starting model. We observe the Ventura anticline on the western side of our cross-section, fitting local scale measurements, and we can also see contrast across multiple faults near the surface and at depth. We observe soft sediments in the Eastern California shear zone and west of the San Andreas Fault. We realized our result needed improvement in the shallowest portion, or less than 0.5 kilometers depth. This is critical as this impacts the amount of shaking during an earthquake. Here we are showing footage of the recent 2019 ridge crest events, including a satellite before-after of the ruptured surface and the shaking in a grocery store during the magnitude 6.4 event. Our specific goals are to gain constraint on the near surface. Here I am showing a VS30, or average shear velocity in the upper 30 meters, using Wills and Clayhan 2006 data based on geology and borehole measurements. We aim to also go beyond imaging shear velocity and obtain VP-VS ratios in the subsurface, or the compressive to shear velocity ratio. The solution to our objective is to add a dataset, receiver functions. Receiver functions use faraway teleseismic earthquakes and P to S conversions created by structural contrasts through deconvolution. This effectively removes the path and source information to give a sensitivity to near-station horizontal interfaces, such as the MOHO, which is the boundary between the crust and the mantle, and the sediment to bedrock interface. Professor Vera Schultz-Pelcom at CU Boulder provided us receiver functions across the region using 16 years of earthquake events recorded across Southern California. This analysis is mainly possible by Vera's work and the continuous efforts of SCEC and SoCal institutions to provide high-quality data. Receiver functions typically have a zero-time peak, and then later arrivals denoting crust and MOHO or other interface structures. However, many of the stations in Southern California appeared messy and had later, more complex early arrivals. Most individuals, including one of my committee members, typically throw these stations and measurements away, especially as this can mask later arrivals from the MOHO. However, we are focused on the near surface. It has been shown that these complex early arrivals can be modeled and are due to sharp boundaries between slow sediments and hard bedrock, and are also influenced by the VP-VS ratio. For example, fluid-filled sediments will have a higher VP-VS ratio. So we decided to focus on just the initial peak. We mapped up the delay time of the initial peak in the first 2 seconds of the receiver function for every station. The underneath map is just the interpolated result between stations. For station BAK in the heart of the South Central Valley, you can see the main peak arrives right around 2 seconds, which fits with our mapped up result. This is interesting, and we see major peaks in sediments similar to another map we looked at earlier. The short period HRV data is strikingly similar to the receiver function data. Next, we plotted up HRV at each station for 7 seconds period and versus the receiver function delay time. There's a clear, measurable, strong correlation between the two data sets. We also colored these according to the nearest VS30 measurement, and we see lower HRV and earlier receiver function peak arrivals in the mountains, which are teal in color, and higher HRV and later receiver function peak arrivals in the sediments, which are more red in color. Next, we performed our inversion, and we will start with an example at the Star Station at the edge of the Los Angeles Basin. We used our previous result as our starting model, so we didn't have to search too far. Our model space now consists of both shear velocity and VP over VS ratio for this top linear layer. I have shown our starting model in both spaces in red, and we use the Brochet empirical formulas to have a first guess estimate of VPVS from the average VS in the top linear layer. Our data includes the first 2 seconds, which are outlined in purple here, of the receiver function, and the shorter periods of the HRV shown as period versus HRV, and phase velocity shown as period versus phase velocity for the shorter periods. Our data is shown in black and the starting model in red. Here's our posterior if we do not include receiver function data. You can see that we are struggling to find a good model. Additionally, we have wide dispersion of VP-VS ratio measurements. Once again, we include receiver functions, but we tighten up our results in both VS and VP-VS. But most importantly, we fit the receiver function data. We also include our final mean model, which are the gold squares, and the minimum misfit model, which are the white circles. As per usual, we do this for every station and obtain a shear velocity model and a VP-VS ratio for the top linear layer. Here's our shear velocity model at the surface and at 1 kilometer depth. We also show the CVMS geotechnical layer at 0 kilometer depth. You can see our results are similar in color in the Los Angeles Basin, but we gain additional constraint with our result beyond the Los Angeles Basin, where the geotechnical layer has poor resolution. Specifically, we observe low shear velocity in the basins, high shear velocity in the mountains, and low shear velocity in the northwest corner of the Eastern California shear zone. We also observe strong across-fault contrasts. We allowed our linear layer to vary in size, so here we are only looking at results with stations with a relatively thick top layer. Our near-surface VPVS result contains higher VPVS in basins, typical and expected for fluid-saturated sediments. We also show low VPVS with values typical of felsic granitic material of continental origin in the Sierra Nevada ranges. In comparison, in the Peninsula ranges, we see values more typical of mafic material or oceanic origin. Both of these fit the local surface geology. We also observe higher VPVS ratios along portions of the San Andreas Fault and in the Eastern California shear zone, which we associate with fractures that promote reduction in shear velocity. We also observe that the Los Angeles Basin has a deeper section corresponding to higher VPVS. This suggests that the receiver function requires both to occur. There's not a trade-off between the two. We also observe deeper and shallower basins accurate to previous local studies. We have a cross-section AA prime, which highlights the deeper part of the LA Basin is southwest of the Newport-Inglewood Fault. We also observe shallower sediments northeast of the San Andreas Fault. We have higher VPVS in deeper parts of the Los Angeles Basin and in the Eastern California shear zone. When comparing the top layer average VS to the expected empirical result by Brochet 2005 for the VPVS ratio versus our result, we see overall lower than expected VPVS ratios, which suggest widespread fracturing and or low fluid saturation outside of the basins. This is consistent to lab studies where prominently low measurements were found from greater than 45% of surface samples published in Zaitsev et al. In 2017. Next, we move from Southern California up the west coast to Alaska. One of the main motivating factors to analyze the Alaska subsurface was the incredible EarthScope Alaska Transportable Array. Hardworking scientists flew to remote regions to deploy these instruments, which ran for multiple years. In the bottom left, we have a time lapse of what setting up one of these seismic stations looks like. 4 people are required, not including the helicopter pilots. Beyond station availability, Alaska is also a complex region. Alaska consists of a mosaic of accreted terrains, each impacting the others. It also has a Pacific plate subducting beneath the North American plate, with different rates in the Aleutians compared to the Gulf of Alaska, because new oceanic crust is originated to the south and hinges out to the subduction zone marked in magenta here. Alaska also has active volcanoes from the subducting Pacific plate in some areas, like the Aleutians, and dormant volcanoes in others, like the Denali Volcanic Gap. Basically, when the oceanic plate subducts and reaches a certain depth, the fluids and overriding material is pressurized and forms a magma chamber that then becomes a volcano. Additionally, Alaska has an overriding Yakutat terrain that accreted recently and further impacts the movement of material within southern Alaska, acting as a geologic snowplow. Our main goal is to use the Alaska TA stations to capture the entire region from the near surface into the upper mantle. We will use all of the data sets we have previously discussed and the Markov chain Monte Carlo inversion. Our driving questions are, what is the crustal thickness across the different terrains? What do we see where the Pacific plate is going down beneath Alaska? What can we learn about volcanism? And can we resolve near-surface basin structures on a regional scale? Here we are showing Alaska, major basins, faults, and the shaded points are earthquakes. You can see the majority of earthquakes correspond to the downgoing Pacific slab. There have been multiple previous studies that we have the opportunity to learn from and compare results against, but none cover the entire region from the near surface through the upper mantle, so we can add while checking our results. In order to see the upper mantle below the crust, we need to use even longer period, lower frequency Rayleigh waves. We can obtain these frequencies by using teleseismic earthquake data across the Alaska array. Here, for example, we are showing the magnitude 7.5 2018 Indonesia earthquake waves, which are very small and very long period moving across the Alaska TA network. The Rayleigh waves arrive very soon, the R1 arrivals. From both ambient noise and earthquakes, we obtain Rayleigh wave phase velocities. Specifically, we perform iconal tomography, which relates the phase velocity to the spatial derivative of the phase travel time. Helmholtz tomography is similar, but with a minor amplitude correction term that is required for longer period measurements. If we consider station DHY in Alaska as a virtual source and bandpass our signal to focus around 16 seconds period, we can look at the phase travel time estimates of the Rayleigh wave, which is shown as time from 0 is at the DHY station, and then distance from that station for all of these separate receiver stations. We map up this record section spatially, take the derivative, square it, and obtain the phase velocity from this station as a source. We repeat this process for every station as a source and stack up all of our maps for that period to obtain the Rayleigh wave phase velocity map for that period. Here are the final phase velocity maps for iconal tomography and ambient noise cross correlations at 10 and 24 seconds periods, sensitive to approximately 10 to 15 kilometers and 30 to 40 kilometers, and from Helmholtz tomography through Rayleigh waves created by teleseismic events at 24 and 60 second periods. At 10 seconds, we observe basins including the Cook Inlet, Alaskan Shelf, and the Colville Basin. At 24 seconds, we observe thicker crust or slower phase velocities underneath the Brooks Range and in southern Alaska, and faster velocities as we transition from the crust into the upper mantle in central Alaska. At 60 seconds period, we can clearly see the downgoing Pacific slab as this very fast section and possibly cold cratonic mantle to the north. Our particle motion and HRV data are similar to what we did before, but it's critical to look at the waveforms and ensure everything is as expected. Here we are showing the positive part of the cross correlation for virtual source G25K in the Yukon Flats Basin and M20K in the Alaskan Range. The particle motion is shown on the right, where the receiver station M20K is shown here, and the basin station or the source station G25K is shown on the far right. At the source station G25K, we can see the particle motion is elongated radially or horizontally, producing a high HRV ratio at this basin station, where the contrast between soft sediment and bedrock creates an amplified horizontal motion. The result from this analysis for all station pairs is used to obtain the mean HRV ratio at each station. Here we show the results for each station and interpolated onto the underlying grid from ambient noise cross correlations at 10 and 24-second periods, as well as from teleseisms at 24 and 60-second periods. We observe higher HRV ratio in the sedimentary basins, including the Colville and Cook Inlet basins, and lower HRV in crystalline rock in the Brooks Range. Our 1D Markov chain Monte Carlo inversion consists of our shear velocity model. Here I'm showing depth of the top 10 kilometers versus shear velocity and stretching from the surface all the way down to 150 kilometers versus shear velocity. Our data consists of the receiver function, phase velocity, and HRV ratios. Our starting model and expected results are shown in red, and our actual data is in black. For station G23K in the Northern Ray Mountains, you can see that our initial model from a global diffraction model from Shapiro and Ritzwaller 2004 does not match our data at shorter periods or the receiver function. First, we will take a look at what only phase velocity data can provide for us. Each posterior model is shown here in cyan, and each corresponding forward model predicted data is also included. Next, we will look at the impact of including receiver function data from our inversion. Now we obtain a much tighter posterior, but we are still not fitting the HRV data, especially at shorter periods. Additionally, this appears to be a bit slow, considering the station is in the Northern Ray Mountains. This, in conjunction with the broad posterior near the surface, suggests that we lack sensitivity without incorporating the HRV ratio data. As you can see, if we include all data sets, we obtain the tightest posterior distribution, fit all of our data sets, and capture what we expect near the surface, faster shear velocities for this station. We use the minimum misfit model shown in white as our final result at each station. As per usual, we apply this to every station to obtain a shear velocity model for the region. Our final results at each station, interpolated onto the underlying grid, are shown here at 1, 25, 45, and 100 kilometer depths. We observe basin features at shallower depths and crustal thickness variations at 25 and 45 kilometer depths. We also observe the downgoing slab, warm asthenosphere, and cold cratonic mantle in the north at 100 kilometer depths. But we don't stop here. This is just our jumping off point for a follow-up inversion. Next, we use a Gaussian smoothed interpolated model and perform a follow-up inversion with the phase velocity data, as this is sensitive to structure between stations. We use high damping so that we don't stray too far from our model that we previously determined. The results are shown here on the left, and you can see some of the regions are more tightly constrained than before. We also include an outline of the Yakutat terrain as previously mapped by Eberhard Phillips. Specifically, we observe low shear velocities in the Cook Inlet and Colville Basin, as well as across all major basins, the Yukon Flats, Copper Basin, off the Alaskan Shelf, etc. At 25 kilometers depth, we can see the Wrangell volcanic field really pop up here, which is very, very interesting, and thicker crust beneath the Brooks Range. At 45 kilometers depth, we see the thinner crust in the North Slope and in central Alaska. We also observe a slope feature that has previously been attributed to a mantle wedge. At 100 kilometer depth, we see the cold mantle in the North Slope, the downgoing Pacific slab, and we have also included all earthquakes to highlight this Pacific slab here. Additionally, we see slower asthenosphere or warmer, slower colors on the western and eastern sides. We also analyze MOHA depth, or depth to the crust to upper mantle transition. From this, we can see thicker crust beneath the Brooks Range, as it's deeper here, and then thinner crust in the Yukon Composite Terrane, or the central area. We also see that it's very complicated south of Denali Fault because of the mantle wedge. We also have a few cross sections focused in the upper 10 kilometers and from the surface to 150 kilometer depths. A8 prime, which stretches from the Seaward Peninsula across the Brooks Range and into the Colville Basin, captures the Foreland Basin, which gets deeper towards the Brooks Range, thick crust beneath the Brooks Range, and shallow sediments in the Selawik Trough, and warm asthenosphere below the Seaward Peninsula. EE prime spans from the Gulf of Alaska to the Colville Basin in the North Slope. We similarly image the slow sediments in the Colville Basin and smaller, shallower basins. We also see the mantle wedge-like structure above and intersecting the mapped downgoing Pacific slab, shown as a fast purple. You can also see the warm asthenosphere is disconnected from this area. In C prime, from the southwest to the northeast, we see major basins and the mantle wedge structure. You can also see the high number of earthquakes on the western side compared to the eastern side. Both have warm asthenosphere that could feed into volcanic structures. In DD prime, from the Kodiak Shelf to the northeast, we cross the Wrangell volcanic field. We can see the mantle wedge structure, but also evidence for asthenosphere butting up against the Yakutat terrane to create toroidal motion and feed the Wrangell volcanic system. In conclusion, we have provided new models of Southern California and Alaska with increased resolution and certainty by including surface wave phase velocity, HRV ratio, and receiver function datasets. We perform a Bayesian Markov chain Monte Carlo inversion that quantifies sensitivity and uncertainty. In Southern California, we are able to image basins and mountains, match local scale studies, and by including receiver function data, we are able to obtain VP-VS ratios in addition to shear velocity in the near surface. In Alaska, we image basins, volcanic regions, and mountains. Overall, we see crustal variations related to geological terrains. My research was made possible by work from many previous scientists, a few of which I highlight and referenced within this presentation. I am hosting this conversation in the traditional territories of Goshute, Eastern Shoshone, Ute, Paiute, Navajo, and others. We also recognize that many peoples' various origins have been displaced onto and within these lands. Our Southern California study occurred in the lands of Niue, Paiute, Mojave, Tonga, and others. Our Alaska study occurred in the lands of Inupiat, Tanana, Denenda, Yupik, and others. We also recognize that many people of various origins have been displaced onto and within these lands. Finally, thanks to all of you. My PhD research would not have been possible without your ongoing support, inspiration, motivation. I especially thank my advisor, Professor Fanchi Lin, for his guidance, encouragement, and scientific inspiration during the past 5+ years. I also thank my committee members, Mir Alam, Mike Thorne, Pete Lippert, and Yehuda Ben Zion. All of you have been incredible role models and inspiring scientists. I thank all of my friends and mentors within University of Utah and beyond at Sandia National Labs and at Ludwig Maximilian Universität. Thank you to all of my friends, family, spouse Elliot Berg, and many mentors throughout the years. And thank you especially to all of my friends and family from my hometown of Fargo, North Dakota. All of your unwavering support and encouragement propelled me to where I am today. Thank you for your time and attention. If you would like further information on our 2020 Alaska and 2018 Southern California studies, these are published through JGR Solid Earth and models are available on IRIS. Our second California study, including VP-VS ratios and receiver functions, has been submitted to the Journal of Geophysical Research Letters. Thanks again.